In this video, we will continue our discussion of the multi-step synthesis of organic compounds. However, we will be utilizing the new reactions to polar pi bonds that we have been learning in the past couple of weeks as the key bond-forming steps in these synthetic schemes. We will continue to identify synthetic traps. A synthetic trap is simply when a transformation is proposed, but some undesired reactivity happens instead. And this often occurs due to functional group incompatibility. Finally, we will learn how to apply protecting group schemes to address these issues of functional group incompatibility. For example, when two functional groups will react with each other instead of undergoing the desired reactivity, we will protect or mask one of them. Although our primary goal today is to propose multi-step syntheses to a desired product from some given starting material, including reagents and all synthetic intermediates in between. We will also be learning some new reactions. Those reactions that we are learning today did not fit neatly into the patterns that we've learned so far, but are very important for synthesis. These reactions include the synthesis of organometallic reagents. So far, we've learned about 3 types of organometallic reagents: Grignard reagents, organolithium reagents, and cuprates. And although depending on the R group, so what the alkyl group actually is, many of these can be bought at the chemical store, sometimes a synthetic chemist needs to make them from other readily available compounds. So we'll learn how to do that. It's pretty straightforward. We need to learn some oxidation reactions. We've already learned how to reduce aldehydes and ketones via nucleophilic addition. In organic chemistry, reduction means reducing the number of bonds between carbon and more electronegative atoms, usually oxygen. The opposite process, oxidation, can also be effected using different reagents that will increase the number of bonds between oxygen and carbon from 1 in the alcohol to 2 in the ketone, for example. Today we will learn what these reagents are. We will then learn a different type of reduction reaction. This type of reduction reaction is primarily used for nonpolar pi bonds, actually, like alkynes and alkenes. And this is called hydrogenation. In hydrogenation reactions, H2 is added across the 2 carbons of a pi bond. In the case of an alkyne, that can happen twice, first to generate an alkene, and then again to generate an alkane. So 2 equivalents of H2 can be added. And don't worry, we'll talk about this reaction in detail shortly. Finally, we'll interrupt the protection of alcohols, so stay tuned for that. We'll evaluate functional group compatibility and think about utilizing selective reactions, reactions where there may be 2 functional groups that may react, but we can use some special conditions or a special reagent so that only one reaction takes place, favoring one product. We'll be learning a few new reactions and we'll be doing a lot of practice problems. But remember step 1, don't panic. We're going to go through it step by step, so we just need to stay calm and use our chemical intuition. I've listed the new reactions here, and let's get started. We'll start with a problem. Propose a synthesis of the desired product from the given starting materials. Take a moment, pause, and try this yourself now. It'll be very important today that you play along, that you pause and try the problems and then listen to the video. And you won't necessarily be able to propose every single synthesis that I ask you to, but I want you to get started so that hopefully you can come up with the problem that we're going to solve in the next part of the video. Okay, so try this synthesis. Whenever we're solving synthesis problems, we employ retrosynthetic analysis. Retrosynthetic analysis just means, like it sounds, thinking backwards. For example, look at the product and identify the functional groups. there is a secondary alcohol. How do I know to make secondary alcohols? Well, my brain starts to go. There are many ways to make secondary alcohols. Hydration of alkenes, for example, substitution reactions. Looking at my starting material, neither of these seem like a good idea or a good fit for the starting material that is given to us. Continuing to activate the knowledge that I have from spending so much time with my reaction charts, I recall that secondary alcohols can be made by reduction of ketones, as well as from Grignard addition to aldehydes. At this point, I've come up with several different ideas, several different ways to make secondary alcohols. And I'm thinking that these two are not a good fit, but I need to think a bit more deeply now. Let's take a look at the product and think about what bonds may be made or broken. It does seem like this carbon is probably this carbon in the starting material. And if that's the case, then this carbon-carbon bond has been made. Now, this problem is a bit tricky because it says all of the carbons must come from benzyl alcohol. Thinking about the bond that I have identified as being made in the product, and looking at the ways to make secondary alcohols that I've listed either on paper or mentally from my reaction chart, it looks like this way is the best fit. The Grignard addition to aldehydes to generate carbon-carbon bonds. Now that I've identified a good synthetic route or a good possibility, I'm going to draw out what the specific aldehyde and the specific Grignard reagent will look like to generate this desired product. This part of the molecule will result from an aldehyde to which a Grignard reagent has added, generating the key carbon-carbon bond that we've already identified by this nucleophilic addition step. That will generate that bond. The rest of the atoms, the CH2 group and the phenyl ring, all together called a benzyl group, they would end up here. This looks great. I think that this will work. However, now I need to ask myself, how can we generate those key intermediates that we have come up with via retrosynthetic analysis from this starting material given? It looks like the alcohol, it's a primary alcohol starting material, must undergo oxidation. So look, there's two hydrogens in the primary alcohol, one hydrogen in the aldehyde, one bond between carbon and oxygen in the alcohol, two bonds between carbon and oxygen in the aldehyde. So that's an oxidation process. So the primary alcohol must undergo oxidation to generate this desired aldehyde for the Grignard addition reaction, that key bond forming step that we have identified. We don't know most of us do not know the reagents to affect this transformation yet. So we're going to need to learn those reagents. And then it seems that we need to generate a Grignard reagent from an alcohol. So we need to learn how to make organometallic reagents such as Grignard reagents. All right, we have two types of reactions we need to learn, and then we can complete this problem. Let's get to it. We will first learn how to synthesize organometallic reagents. As I've mentioned, often one can buy organometallic reagents at the chemical store, but they can also be made when necessary. I have listed three types of organometallic reagents that we will interact with in this course. Organomagnesium reagents, otherwise known as Grignard reagents, organolithium reagents, where there is a carbon-lithium bond, and dialkyl cuprate reagents, such as this one. We'll start with Grignard reagents. Grignard reagents are made from alkyl bromides. They can also be made from alkyl chlorides or alkyl iodides by the same process, but then instead of bromide being incorporated into the product, it would be chloride or iodide. And it doesn't particularly matter for the purposes of our class whether or not you generate organomagnesium bromides or organomagnesium chlorides. Solid magnesium metal is added to the alkyl halide and reduces the carbon bromide bond. This reduction is thought to occur via single electron processes known as radicals. So we will not be learning the curved arrow mechanism for this transformation. And just to review, once the Grignard reagent is formed, we think about the carbon making the bond to magnesium as having lots of carbanion character. Okay, so that carbon making the bond to magnesium has carbanion-like character. And because it has carbanion-like character, the solvent for this reaction is specified. So it's diethyl ether, and it's chosen as the solvent for this reaction for a couple of reasons. I'm going to stick to the reason that's easiest to understand and most pertinent for us. This is an organic solvent that is anhydrous. In fact, you need to make sure that the diethyl ether that you use is anhydrous without water before trying to generate the Grignard reagent. And that's because since the Grignard reagent has carbanion-like character, it is very basic. In fact, if the Grignard reagent encounters water, it will act as a base, deprotonate water, generating an alkane and hydroxide. Water, the acid on the left, has a pKa of 16. An alkane, the acid on the right, has a pKa of a million? No, let's say 45. So that means that the equilibrium constant for this process will be 10 to the 30th power. Whoa, that is way greater than 1. If this proton transfer reaction occurs, then a boring old alkane is formed. It is no longer nucleophilic. It is no longer anything useful except for burning. So Grignard reagents need to be kept under anhydrous conditions, away from proton sources. It is important that when you make Grignard reagents on paper or in lab that you do specify solid magnesium metal and diethyl ether, or another ether if you want. You can use tetrahydrofuran, the cyclic ether. It is often used instead of diethyl ether in these reactions. But you need to specify some sort of ether solvent because it's important to me that you remember that anhydrous conditions are key when working with Grignard reagents. Now, many of the same aspects of forming Grignard reagents apply to forming organolithium reagents and dialkyl cuprates. To form organolithium reagents, again, an alkyl bromide is the starting material, whereas magnesium was used as the reductant when a Grignard reagent, an organomagnesium reagent, was desired. Lithium metal is used as the reductant when an organolithium reagent is desired. We see once again that diethyl ether is specified as the solvent. It is important that this reaction be kept under anhydrous conditions, that the organolithium reagent, which is basic just like the Grignard reagent, is kept away from proton sources such as water. Following reduction of the carbon-bromide bond, there is a carbon-lithium bond, and the carbon bonded to lithium has carbanion character, just like for the Grignard reagent. Finally, to form dialkyl cuprate reagents, you actually would start with organolithium reagents. So if the diethyl cuprate is desired, one starts with ethyl bromide, generates ethyl lithium, and then treats 2 equivalents of ethyl lithium with copper iodide to generate the cuprate. So essentially, copper replaces the lithium to generate the cuprate. The carbons bonded to copper do have anionic character. When this cuprate does react with some electrophile, such as an alpha-beta unsaturated ketone, it only donates one of the alkyl groups. So after workup, which protonates the enolate intermediate, we see the 2 carbons have been added to that alpha-beta unsaturated ketone in a conjugate addition, which we've already learned. So one of the alkyl groups adds, but the other alkyl group is wasted. It's not added. This is not a big deal if the alkyl groups are, say, ethyl groups. So one is added, the other is wasted. But the more and more carbon atoms that are bonded to the to the copper. So the more and more complicated cuprate, so let's say this R group is really big and complicated, then that's a bigger deal. That one of an entire equivalent of carbanion has been wasted. It's been thrown out with the waste. That's a bigger deal. So that is a negative aspect of cuprates. But we know that cuprate reagents are the only organometallic reagents that we know of that do this conjugate addition that add to the beta carbon of an alpha beta unsaturated ketone. So they are very useful, but we do want to keep in mind that sometimes they're quite wasteful. You might notice that this time I've written the cyclic ether as the solvent here. For our purposes, it doesn't particularly matter whether or not you invoke diethyl ether or THF, tetrahydrofuran, as the solvent, but for all of these reactions, an ether solvent is required, both because of the requirement for anhydrous conditions, but also this type of coordinating solvent is important in these reactions. By coordinating, I just mean that there are lone pairs, and we won't worry too much more about it beyond that, although you can always ask me if you want more details. We've used the past several minutes to discuss not only the formation of organometallic reagents, but also some of their uses and aspects of their reactivity that we may have forgotten. As we are about to move on, let's consider two more aspects of organometallic reagents. Before I get to the prompt on this screen, let's review the relative reactivity of organometallic reagents. Can you arrange organolithiums, organocuprates, and Grignard reagents from most reactive to least reactive? Yes, the most reactive is the organolithium, then the organomagnesium species, Grignard reagents, and finally the dialkyl cuprates. These reactions to form organomagnesium and organolithium reagents are often called Umpelung, and I know I did not pronounce that right if anyone speaks German, transformations. Now this word, Umpelung, again, not pronounced correctly, refers to a reversal in polarity. The carbon bearing the alkyl halide functional group has a partial positive charge, whereas after reaction with magnesium, the insertion of magnesium into that carbon-bromine bond, that carbon ends up with a partial negative charge. The alkyl halide is an electrophile. It reacts with nucleophiles. On its own, we know if we treated it, say, with a good nucleophile like cyanide, it would undergo an SN2 reaction. The organomagnesium species has the total opposite reactivity, right? It's nucleophilic, it's electron poor. Magnesium has added electrons into that carbon-bromine bond. So instead of reacting with nucleophiles, organometallic reagents react with electrophiles such as epoxides, or in this case, I've drawn a carbonyl compound, a ketone. I think we've quite thoroughly discussed now how to make organometallic reagents, which, one more time, serve as sources of nucleophilic carbon. Ironically, made from sources of electrophilic carbon. I bet that we are 100% able now to provide the reagents necessary to convert this alcohol into the Grignard reagent. So if you like to pause and you like to add that part, you like to solve this part of the puzzle right now, please feel free to do so. I'm going to move on to talk about oxidation of alcohols to aldehydes and ketones, and then we will together put together both pieces of the puzzle. Before we get to oxidation, let's take a moment and review what we already know, which is how to reduce aldehydes and ketones to alcohols. Please pause and list the reactions that you know to affect the reductions of aldehydes and ketones in this space, and then rejoin me. Ketones and aldehydes can be reduced by nucleophilic addition of hydride to the electrophilic carbonyl carbon, as we've previously learned. Ketones are converted to secondary alcohols by addition of hydride, and And that's simply because ketones start out with two alkyl groups, and so they're going to end up with two alkyl groups. It might be important to keep track of the carbonyl carbon as it changes in these addition reactions, particularly as we are thinking about synthesis problems. Mapping out carbons and understanding where they came from is particularly important. Aldehydes also undergo these transformations to generate primary alcohols, and that is simply because they start out with one alkyl group compared to the two alkyl groups of ketones, and so they end up with one alkyl group. They will be primary alcohols. In addition to the nucleophilic addition of hydride to reduce aldehydes and ketones, Grignard additions also represent reduction reactions as the number of bonds between carbon and oxygen decreases in these transformations. Taking a look at the reduction of the ketone here with a Grignard reagent, there are two bonds between carbon and oxygen. After the Grignard reagent adds, there is one bond. So this is a reduction reaction. Again, it might be important to keep track of the carbonyl carbon as it undergoes these transformations, since we will be thinking backwards. We will want to look at tertiary alcohols and say, well, what ketones, what carbonyl compounds, plus what Grignard reagents could this molecule be made from? So make sure you can keep track of the carbonyl carbon as it undergoes these transformations. Now that we've reviewed the reduction reactions of aldehydes and ketones, let's learn the oxidation reaction. What we will find is that primary alcohols can be oxidized to aldehydes. Overall, what is happening in this transformation is that the oxidant, whatever this magical species might be, and we'll worry about the exact chemical identity of the oxidant later, it is removing hydride from the carbon that becomes the aldehyde carbon. The alcohol contains one bond between the carbon and oxygen, whereas the aldehyde contains two. So this is an oxidation reaction. Now, under some conditions, that same magical oxidant, whose chemical identity we will learn later, some of those oxidants, they may continue to oxidize that carbonyl carbon by removing another equivalent of hydride to generate a functional group that we have not talked very much about yet, and that is the carboxylic acid. Now, there are three bonds between the carbonyl carbon and oxygen. It's just two different oxygens, but it's still 1, 2, 3 bonds representing an oxidation relative to the two bonds between that carbonyl carbon and oxygen in the aldehyde. So we will find that primary alcohols can be oxidized to aldehydes and under some conditions all the way to carboxylic acids. We'll worry about the details momentarily. Right now, we're just thinking. Secondary alcohols can be oxidized to ketones via removal of the one hydrogen atom bonded to the carbon bearing the alcohol functional group that becomes the carbonyl carbon. Again, we'll worry about the specific oxidant in just a moment. In this process, we observe one bond between carbon and oxygen being converted to two bonds, representing an oxidation process. Now, because the secondary alcohol begins with two R groups, ending up with those two alkyl groups maintained in the ketone, it's a bit difficult to imagine further oxidation of the ketone. Unlike the aldehyde, which had another hydrogen atom that could be removed as hydride to form the carboxylic acid, the ketone does not have a hydrogen atom bonded to the carbonyl carbon, it has two alkyl groups. So it is difficult to imagine further oxidation of the ketone unless the R group could somehow be removed and replaced with an oxygen atom. No way, you might say. That could never happen. Well, we'll stay tuned. It's not happening today. Now that we have thought through the various possibilities and the overall bonds being made and broken in oxidation reactions of alcohols, let's begin to learn the reagents. Let's learn what I meant by O, the specific oxidants that we will encounter when considering these transformations. What we will begin with is just the overall big time oxidation of primary alcohols to carboxylic acids. So now both of these hydrogen atoms bonded to the carbon bearing the alcohol that becomes the carbonyl carbon. Both of those hydrogen atoms were moved as hydride. This represents going all the way from the primary alcohol to the carboxylic acid. One bond between carbon and oxygen to three bonds between carbon and oxygen. The reagents that will affect these conditions are listed here. And yes, you do need to know all of them. And not because I'm trying to be mean, but because you will encounter these different oxidation conditions either in textbooks, on the MCAT, on standardized exams. You do need to be familiar with all three sets of reaction conditions that will affect this transformation. Now, what you'll see that they have in common is there is some metal, chromium in the case of the first two sets of conditions. And I will say this second set of conditions basically generates the first set. So they're pretty similar. And then this third reagent here does not contain chromium, but it does contain manganese. So we have a transition metal oxidant in all three cases. I will point out that this potassium permanganate oxidation was a common question on the MCAT before they decreased the amount of organic chemistry on it. So I can't speak for how common it is on the new MCAT, but in the past, this reagent did show up. So if you're going to take the MCAT one day, that's the test that pre-medical students take, then make sure that you remember these reagents. Although you are not responsible for drawing the complete curved arrow mechanisms for these transformations, you may be wondering why the alcohol is oxidized twice to the carboxylic acid. And you can understand much of the arrow pushing for that phenomena. The primary alcohol is first oxidized by chromium or manganese to generate the aldehyde. Now, you'll notice something if you take a look at the conditions. Each set of conditions is aqueous, or at very least has water around. The top two sets of conditions are under acidic aqueous conditions, whereas the potassium permanganate oxidation is under basic aqueous conditions. Either when there's an acid catalyst and water around or a basic catalyst and water around, you know that aldehydes are in equilibrium with what? Or hydrates. Just take a look at the hydrate. A hydrate looks really similar to the alcohol. I bet when you first encounter hydrates, you may have even called them alcohols or called them double alcohols or something. And we know they're different, right? They're very, very different. The carbon making the hydrate, they used to be the carbonyl carbon. It is much, much different than a normal alcohol carbon. It behaves differently. It undergoes addition, elimination mechanisms. It does not undergo substitution, for example. It's different, but it does look pretty similar to the alcohol. And so from the hydrate, these oxidants can remove that second equivalent of hydride. It's removed from the hydrate, it is not removed from the aldehyde. So understanding that allows us to consider the next question, which is, well, what if we didn't want to oxidize all the way to the carboxylic acid? What if we desired in our synthesis just to generate the aldehyde? Could we stop at the aldehyde? Now, the answer is no under aqueous conditions. Under aqueous conditions, you cannot prevent formation of the hydrate, and thus the oxidation will proceed all the way to the carboxylic acid. So the problem here is water. And the answer to stopping at the aldehyde will simply be oxidations in the absence of water, so anhydrous oxidations. Chemists have developed conditions for the anhydrous oxidation of primary alcohols. The key reagent is called PCC. Well, what in the world is PCC? PCC stands for pyridinium chlorochromate. Pyridinium chlorochromate. So it's a salt of chromate, basically, chlorochromate. And chromate, that sounds like chromium. Yes, so we have a chromium 6 oxidant, but there's no water around. And you can see we're using an organic solvent here. And because there is no water around, there's no hydrate formed. So after that first oxidation of the primary alcohol to the aldehyde, The hydrate is not formed. That required water and an acid or base catalyst. It's not formed. So if it's not formed, no further oxidation will occur. That hydrogen atom will be retained, and we can see it there in the aldehyde. Excellent. So now you should stop. You should stop, and you need to enter 2 new entries into your reaction chart. So alcohols to carboxylic acids, and you should write down all 3 sets of conditions because you'll encounter all 3. And then alcohols to aldehydes using PCC, which is simply a form of this chromium-6 oxidant that is soluble in organic solvents due to being this pyridinium salt, and we're not going to worry about the specifics any more than that. Once you have those entries into your reaction chart, let's just briefly talk about oxidation reactions of secondary alcohols. Now, as we said, when we were engaging in our lengthy thought exercise about what the oxidations of alcohols might look like, the ketone only has this one hydride, one hydrogen atom bonded to the carbonyl carbon. So right now, it's hard to imagine it undergoing any further oxidation past the ketone. So whereas oxidations of primary alcohols were tricky, oxidations of secondary alcohols are really not tricky at all. You're welcome to use any of these 4 sets of conditions. The top 3, these were the aqueous conditions. They converted primary alcohols all the way to carboxylic acids. But look at the ketone. The ketone doesn't have any hydrogens. Whoa, that looks crazy. So it can't go any further. So those aqueous conditions are okay. Or the dry conditions that for the primary alcohol resulted in formation of the aldehyde, avoiding the hydrate intermediate. Of course, under any of the aqueous conditions, the hydrate of this ketone product is certainly formed. Because that secondary alcohol began with 2 R groups, it still has 2 R groups. There's no hydride here to remove. So that's what I mean. No further oxidation is possible. Now, does that mean that you can use any of these 4 conditions all the time with no worries whatsoever? What do you think? No, it doesn't mean that because there will often be more than one functional group in a molecule, and perhaps that functional group is sensitive to these oxidation conditions. So really, what set of conditions you use now will depend on the nature of the R group. For example, the first 2 sets of conditions involving chromium, those reactions are conducted under acidic aqueous conditions. So if one of these R groups has a functional group that is sensitive to acidic aqueous conditions, like let's say there's an acetal in one of those R groups, well, acidic aqueous conditions, that's going to remove the acetal. So maybe you don't want to do that. So then if that's the case, if there's a functional group that is sensitive to acidic conditions, then you would avoid those top 2 oxidation conditions. You might use the potassium permanganate conditions, which are basic aqueous solution. Or maybe there's another group that is sensitive to base, in which case you could use the PCC oxidation because that is conducted under neutral conditions in an organic solvent, so no water. So although we're not worried about any further oxidation for a secondary alcohol, we might have to worry about reactivity in the R groups, and sometimes you'll have to choose a specific set of conditions rather than just picking one at random, but you'll be fine. You'll learn how to evaluate those situations. Well, the good news is we are finally ready to solve this problem. So go back to this problem, or if you're following along in the slides, you have a clean version, and propose a synthesis of the desired product from the given starting material. Like I said about 30 minutes ago, it is extremely important that you pause and play along to make sure that you apply what you just learned. You solidify the past 30 minutes in your hippocampus and learn how to apply that material, use that material in solving synthesis problems. Otherwise, this has been a total waste of your time. So if you'd like, just set a timer, give yourself 5 minutes, try it out, and then come back. To briefly recap our retrosynthetic analysis, we identified the secondary alcohol in this desired product. We also identified that this carbon is probably that carbon in the product and that this bond was made. We remembered that secondary alcohols can be generated via Grignard additions to aldehydes. This combination of aldehyde and Grignard reagent, once they are mixed together and then subjected to an acidic aqueous workup, is expected to generate the desired product, where the benzyl magnesium bromide delivers these carbons and the rest of the atoms come from the aldehyde. When we first analyzed this problem, we did not know how to oxidize primary alcohols to aldehydes, but now we do. The oxidation of primary alcohols to aldehydes is conducted with an anhydrous chromium oxidant, PCC, and an organic solvent, typically methylene chloride. Now we need to generate the Grignard reagent. We know that Grignard reagents are made from alkyl bromides. This transformation is achieved by adding solid magnesium metal to the alkyl halide. Magnesium inserts into the carbon-bromine bond, generating the anionic Grignard reagent. To convert benzyl alcohol to benzyl bromide, we will rely upon a reaction we learned in Organic Chemistry 1, which is that treatment of primary alcohols with phosphorus tribromide affects a substitution reaction, generating the alkyl bromide. Okay, we did it, and we did it by employing retrosynthetic analysis. You will be much more successful if you treat retrosynthetic analysis as a very valuable tool. It will be very hard for you to solve all these problems working in the forward direction. Furthermore, as I told you in Organic Chemistry 1, I do design these problems by thinking backwards, and I never give you a problem that cannot be solved this way. I always say, well, can the students see the key transformation by identifying functional groups and thinking backwards? If that's not the case, I will not ask you the problem. Let's practice this skill of retrosynthetic analysis and try to employ some of these new reactions we've just learned to a different problem. Please, once again, pause and give this a try on your own. If you want, set a timer for 5 minutes. Looking at the product, we identify an aldehyde and an alkene functional group. Taking a look at the starting material, we see that it is our only source of carbon atoms. Looking at the product, we can see there's a total of 6 carbons in it, which suggests that we might need to use 2 molecules of allyl alcohol in our synthesis. It also suggests that this is the key bond that was formed in the reaction, since that would combine 2 of the 3 carbon pieces together. It's possible that some carbons were added different ways or that they were removed. As we move in the class, we'll be able to remove carbons, but right now this seems like a pretty reasonable analysis. Once we have identified that as the key bond formed, we notice that that key bond is formed beta to the aldehyde. That suggests that that bond may have been formed via conjugate addition. The beta carbon is electrophilic. Thus, the other piece, the other atom that made a bond to that beta carbon, that needs to be nucleophilic. Carbanions come from organometallic reagents. We need to remember which organometallic reagent adds to the beta carbon, does a conjugate addition, rather than adding directly to the carbonyl. You've got it, it's the cuprate. Cool, so this will come from a cuprate. Be sure not to add or subtract any carbon atoms here. So this simplifies our problem. Allyl alcohol should be converted to the cuprate, another molecule converted to the aldehyde, and then we'll mix them together in a conjugate addition. So if you'd like to pause and revise or use this new information to try again, please do so. To convert a primary alcohol into an aldehyde requires anhydrous oxidation conditions, PCC, in the presence of an organic solvent. Our first key intermediate has been made. To generate the cuprates, we may remember, looking down at the bottom, that cuprates are made from organolithium reagents. So we'll need to generate the organolithium reagent first. Organolithium reagents are made from alkyl bromides. I am recalling the information found on this slide. Make sure all that's on your reaction chart. The alcohol is converted to the alkyl bromide using phosphorus tribromide. The alkyl bromide is converted to the alkyl lithium reagent using solid lithium metal in an ether solvent. To generate the cuprate, we treat the alkyl lithium reagent with copper iodide, again in an ether solvent. So THF or diethyl ether does not matter. I'm just using the same solvents from the page on which we discussed these reactions. Now the aldehyde and the cuprate should be mixed together. They will undergo a conjugate addition, and we'll need to follow that up with a workup, which will protonate the alpha carbon. And there we go. So our answer to this problem is this part at the top, but we only got there because of our retrosynthetic analysis where we identified the two key intermediates. When you try these problems on your own, please try to use the process that I have modeled for you here. So just going back to our introduction slide, we've learned the synthesis of organometallic reagents, we've learned oxidation reactions, and now it's time to think about hydrogenation reactions. Hydrogenation is exactly what it sounds like. A molecule of hydrogen is added across some pi bond. I'm using X's just to make this really generic. Hydrogenation reactions occur to some polar pi bonds like carbonyls and nitriles, but we know other ways of performing that same exact transformation that I have written here. So adding H2 across the polar CO bond. So we're really not going to discuss hydrogenations of carbonyls very much. However, we will talk quite a bit about the hydrogenation of nonpolar pi bonds, because there is no other way to affect this transformation to nonpolar pi bonds. So aka alkenes and alkynes. So let's take a moment and begin thinking about hydrogenation in the context of alkenes. Alkenes are said to be unsaturated. That's because it's possible for the two carbons making the pi bond, making the double bond, to bond to more hydrogen atoms. So it's unsaturated. It is able to bond to more hydrogen atoms. Alkanes, on the other hand, the carbon atoms in alkanes are making the maximum number of bonds to hydrogen that's possible, and so they are said to be saturated. Alkenes could be making more bonds to hydrogen because the electrons in the pi bond could be bonding to hydrogen instead. And in fact, when an alkene is treated with hydrogen gas in the presence of a metal catalyst, such as palladium adhered to carbon, aka charcoal, the following transformation is observed. An equivalent of hydrogen adds across the two carbons of the alkene to generate an alkane. Now the carbons in the alkane are making the maximum number of bonds possible to hydrogen. Thus, this alkane is saturated. Now, this transformation is technically a reduction because carbons went from bonding to each other, they have the same electronegativity, to bonding with hydrogen instead, and hydrogen is slightly less electronegative than carbon. So this is a reduction reaction of the carbons involved in making the double bond. We've answered these questions here. The last question says, does this reaction even make sense? Well, that's up to you. I would say most of us would think, no, it doesn't make sense. I mean, how are we breaking this hydrogen-hydrogen bond? How does this work? This doesn't make sense. When things don't make sense, we just take a moment and try to make some sense of it using what we know. I will very quickly explain how this reaction takes place. So the key is that palladium catalyst, right? We said, well, the sigma bond in hydrogen is pretty strong. How is it broken and then like magically added to the pi bond? Yeah, well, the palladium catalyst does that. Now, some clever ways to affect hydrogenation reactions have been developed. But the traditional way is to bubble hydrogen gas into a solution of an alkene dissolved in an organic solvent. In this flask is also a solid palladium on carbon catalyst. Now, this is an example of a heterogeneous reaction. Reagents are in all kinds of different phases here. In solution, as gas, as a solid. And in fact, the reaction takes place on the surface of the solid palladium on carbon catalyst, so at the interface between the solution and the solid. When a molecule of hydrogen gas collides with the palladium, palladium can coordinate to the electrons in the sigma bond. And in fact, it can break the sigma bond. So this is called an oxidative addition. And if you're interested in learning more about what's going on here, you should take organometallic chemistry. It's really cool. You can learn all about this. Now, from this palladium-2 species, it was oxidized. Basically, it donated some electrons to hydrogen and it broke the sigma bonds. Once a molecule of alkene collides with the surface of the palladium catalyst that happens to be coordinated to hydrogen, the palladium can coordinate to the pi electrons in the alkene. And that looks like this. Then from here, something very cool can happen. This step is called a reductive elimination. These are all types of elementary steps that you'll learn about if you ever do take organometallic chemistry. So chemistry majors. This is a type of inorganic chemistry, organometallic. It bridges organic and inorganic chemistry, and I really like it. So following that reductive elimination step, what happens is one hydrogen adds to one of the carbons of the alkene. The pi electrons of the alkene accept the other hydrogen, and then palladium gets back those electrons. It goes back to palladium 0. So you can see the catalyst has been regenerated. It is a catalyst. And an alkane has been made. One more important thing to point out here is that during this process, the two hydrogens were added in a syn fashion. Look at this concerted step where the two carbon-hydrogen bonds are made at the same time. They're made at the same time to the same face of the alkane. So in a syn fashion, syn, same. We may not notice the stereochemistry of the addition for acyclic alkenes, such as the one in the example. However, if we subjected this alkene to hydrogenation conditions, we would certainly notice the syn addition of the two hydrogen atoms. If we imagine the two hydrogen atoms add to the top face, then the product will look like this. So they can certainly add to the top face and the bottom face of the alkene with equal probability. But this would be the only stereoisomer product formed. There would not be the stereoisomer of the product where the methyl groups are on different faces, resulting from the hydrogen atoms being on different faces. This anti-isomer, which is just a diastereomer of the one observed, would not be formed. And that is a consequence of the syn addition. Make sure that you understand the hydrogenation of alkenes discussed on these two slides, and let's move on to discuss the hydrogenation of alkynes. As you know, alkynes contain pi bonds and behave similarly to alkenes. What product do you think will be formed when an alkyne is subjected to hydrogenation conditions, such as the ones shown? Be sure you make a prediction. When alkynes undergo hydrogenation, an equivalent of H2 is added in a syn fashion across the two carbons of the alkyne, which are carbons 2 and 3 for this molecule, 2-butene. However, alkenes are even more reactive than alkynes to hydrogenation. We just spent several minutes discussing the hydrogenation of alkenes. Once this alkene is formed, it will just continue to react under these conditions as shown. So it will continue to react to form the alkane, which I've drawn in the zigzag conformation, even though, of course, the hydrogens are added in a syn fashion initially. This is the lowest energy conformation. So two equivalents of H2 have been added across the two carbons of the alkyne. One equivalent in the first addition, and another equivalent in the second addition. So when alkynes are treated under the hydrogenation conditions we have previously discussed, an alkane product will be obtained. All right, cool. We're time to move on? No, not quite. I mean, take a look at this alkene intermediate. What kind of alkene is that? Yeah, that's a cis alkene. Typically, cis alkenes are less stable than the trans alkene isomers, so they're not straightforward to make. We've learned that Wittig reactions can generate cis alkenes, but so far that's the only way of making cis alkenes that we know. E1 and most E2s, many E2s, all E1s though, they will make the more stable isomer, which is usually the trans. So we would like to have some more tools in our toolbox in order to generate cis alkenes. We're synthetic chemists. We need to be able to make anything, and we like options. So would there be any way to just stop this reaction at the cis alkene? Well, not under these conditions. The reaction continues to the alkane. Well, where there's a problem, there's a chemist who is really motivated to solve that problem. And that problem has been solved by, instead of treating the alkyne with just traditional palladium on carbon, it's treated with a special catalyst that has an additive. We call that additive a poison. It makes the catalyst less reactive. So when an alkyne is treated under hydrogenation conditions with a poison catalyst, so Lindlar's catalyst is an example of one of these poison catalysts. Poison just means, again, there's an additive that makes the catalyst less reactive. The cis alkene can be isolated as long as you're paying attention. If you go to lunch and come back 2 days later, and it's probably going to have gone all the way to the alkane, but if you're paying attention, you can isolate the cis alkene. And this is great. We can add this to our list of ways to make the cis alkene. So hydrogenation of alkynes with Lindlar's catalyst, poison catalyst. Awesome. Now, why is a cis alkene formed? We've discussed this because the catalyst adds H2 in a syn fashion in that reductive elimination step that I showed you. By the way, you do not need to memorize this reaction. You do not. This was for fun and because it really does help some students to remember that there's a syn addition. That's the part you have to remember, the syn addition. It helps them to remember that if they know why, and that has to do with this reductive elimination step. But you don't have to memorize that mechanism. That was informational. You do need to know hydrogen adds in a syn fashion. And why is it so exciting that this reaction forms a cis alkene? Well, because we don't know very many ways to make cis alkenes. For those of you who are curious about the poison, one common poison molecule added to the catalyst is called quinoline. And you can see in quinoline this pair of electrons on nitrogen. That pair of electrons can coordinate to palladium, right? And then that slows down the reactivity of palladium. If it's coordinating to quinoline, it cannot coordinate to hydrogen, etc. You just need to remember hydrogen gas and Lindlar's catalyst to affect the hydrogenation of alkynes to cis alkenes. Time to practice. Propose a synthesis of the desired product from the given starting materials. Set a timer for 5 minutes and give it a shot. Identifying the functional groups in the product, we notice a cis alkene and a tertiary alcohol. Cis alkenes can be made from Wittig reactions. And now we also know that hydrogenation of alkynes can generate cis alkenes as well. Taking a quick look up at the starting material, we see that it is our only source of carbon. This alkyne contains 3 carbons. Now, since there's an alkyne and it does look like the 3 carbons of the alkyne map pretty nicely on to the 3 carbons of that cis alkene substituent, we're pretty sure that hydrogenation will be how the cis alkene is generated. Also, we can see that this is probably the bond that's made because it breaks the molecule into 2 3-carbon pieces that could be obtained from this alkyne. Thinking about the tertiary alcohol, there are several ways to make tertiary alcohols. I mean, certainly we could think about electrophilic additions to alkenes. We can also think about Grignard reactions to generate tertiary alcohols. And we've been discussing those today. And just given that we're generating this carbon-carbon bond in the synthesis, it probably makes more sense to make this tertiary alcohol via a Grignard reaction. or some addition of a carbanion, so Grignard or carbanion addition to a ketone or aldehyde ketone. Given that analysis, let's write out the structure of the alkyne that would have been hydrogenated to generate the cis alkene. Okay, it would look like this. So we have 1, 2, 3. That bond needs to be made at some point, and then these 3 carbons here will have to come from another molecule of propyne. From here, let's think backwards one more time and draw out the ketone and the carbanion that would be necessary to generate that key carbon-carbon bond. So now we need to generate both of these species from the given starting material, which is propyne. So we'll go ahead and do that now. In the forward direction, the alkyne can actually be converted directly to the acetylide ion. No Grignard necessary. You may recall from Chem 12A that the pKa of this proton is around 24. So it can be treated with either sodium hydride or sodium amide to cleanly generate the nucleophilic acetylide ion. We have seen this acetylide ion react with alkyl halides, with epoxides. We know it's a good nucleophile. In this synthesis, we're going to react it with a ketone. Let's generate that ketone now. This transformation also involves a reaction learned in Organic Chemistry 1. That reaction is the oxymercuration of alkynes, so the hydration of alkynes, to generate ketones via enols. Where there's been a Markovnikov hydration to the addition of H2O across the 2 carbons of the alkyne. We've now generated both of the key intermediates we identified above. So we're ready to combine them. The acetylide ion will add to the ketone in a nucleophilic addition reaction, just like we learned for, say, cyanide and other nucleophiles. A workup will be needed to protonate the oxygen. You can do a mild acidic workup. At this point, the alkyne has been generated that we identified here, and all that's left to do is to hydrogenate to the final product. Wow, this slide is a mess. Let's work on this over here. Okay, so the desired product looks like this, where there's a cis alkene. So we know to convert alkynes to cis alkenes requires hydrogen gas. That provides the 2 hydrogens that are adding in the syn fashion to the alkyne. In order to stop at the alkyne, a poisoned catalyst is required. You may either write Lindlar's catalyst, or you could write palladium on carbon with the poison. You just need to convey that you understand that it's not normal palladium on carbon. It is a special catalyst, either called by name Lindlar's catalyst, or you write down it's palladium on carbon with a poison. Excellent. We did it. And this particular synthesis involved a few reactions from Organic Chemistry 1, but we were able to get there by thinking backwards, employing retrosynthetic analysis. We're going to try one more problem before we call this part 1 and tackle the rest in part 2. Let's propose a synthesis of this product where acetone is the only carbon source, and then you may use any other reagents you need, but all of the carbons, so 1, 2, 3, 4, 5, 6 carbons in the product, must come from the 3 carbons of acetone. Give it a try. If you gave this problem a try, I really applaud you. This is a really tough problem, and it's a tough problem because it's hard to see the key transformation. We're going to work on it together, though. We're pretty sure that these 3 carbons in the product correspond to these 3 carbons of acetone. That means that a bond was formed right there, and those 3 carbons came from another molecule of acetone. That tells me that the 3 carbon of one molecule made a bond to the 2 carbon of the other molecule. I'm using numbers, but we could use a bit more precise chemical language. Carbon 3 is an alpha carbon. Carbon 2 is a carbonyl carbon. What type of reaction am I suggesting here? Yes, this looks like an aldol reaction has occurred. So if these two molecules undergo a self-aldol, self-condensation, they would generate an alpha beta unsaturated ketone, where the alpha carbon came from the enolate at carbon 3, the beta carbon was the carbonyl carbon, and then a dehydration has occurred to generate the double bond. Looking at the product, we see that it's saturated between these two carbons, the alpha and beta carbons. Unsaturated, saturated. Oh, hydrogenation. So the saturation can be introduced. There's two hydrogens that are now here that were not there before. They can be introduced via hydrogenation. Okay, so hydrogenation conditions essentially a 1,4 addition of hydride to the alpha beta unsaturated species. So just to be sure that we're all seeing it, I'm going to draw the product out again right here below. And then these two hydrogens were added in the hydrogenation. Okay, let's just modify so we can write our reagents down as well. Aldol condensation just requires either an aqueous base or acid. We'll use aqueous base. So aldol, hydrogenation, got the product. Now this was difficult because it is exceedingly difficult to do retrosynthetic analysis to see hydrogenations. So really the key retrosynthesis that we did here was figuring out what this bond was and then thinking, okay, these two atoms that need to make a bond, like that key carbon-carbon bond forming step, how would they do that? And then we recognized the aldol, we drew out what the aldol product would look like, and then we could connect the dots. So very good. As promised, we are going to call this the end of part 1. Let's briefly, before you check out here, let's talk about what we'll do in the next video. So we've learned how to make organometallic reagents, how to affect oxidation reactions, and we learned about hydrogenation reactions. And then we did a ton of practice problems. So we need to talk about protecting group schemes and utilizing selective reactions, and we'll go ahead and do that, do all this stuff in part 2. Okay, see you then.